What, sweetheart? Yeah, me too. It looks like I might be having some trouble with my dot cam and with my webcam for some reason right now. So I don't know how well you guys can hear me. Does the audio sound as it ought to? Do you hear anything strange? Let's see. There we go. Okay. Connect. All right. Sweet. Okay, so we are almost through all of this, guys. I'm really proud of you all for hanging in there and doing as well as you have. We need to talk a little bit more about sequences and series. So that's what we're going to do today. Before I get into that, let me make sure that we've extended the stuff we said we would extend and things are set up how they are. 10, 3, 10, 4, homework 12. This should be it, right? God damn it, what was I? All right, we'll fiddle with that in a little bit. So last time we got to talk about sequences. We got to look at a few families of sequences. Today I just want to look at a few more problems from those to kind of get a feel for how well you guys are assimilating the new notation. And then we're going to talk a little bit about partial sums and start talking about series. It's kind of unfortunate because it's really hard to talk about things like series without this notion of convergence for a sequence. So I wanted to also play around a little bit with some software and help you guys get a feel for what it means for a sequence to converge. Even though it's not an official part of this course, I think it will help a lot when it comes to talking about infinite series, because those are really defined in terms of convergence of sequences. Before we get back to digging in there, though, if there's anything from the parametric equations homework that you guys would like to look at a little bit more, any particular problems in there that were frustrating you, I'd be happy to look at those. Is there anything like that? Yeah, let's see. Oh no, good from your end. Okay, awesome. Oh, you're talking about the audio. Yeah, okay, good. So is there anything from the homework, the previous homework, homework 12, that you guys would like to take a look at before we resume our discussion of sequences and series? Be good, Hamlet. Feeling mostly okay? So then I just want to look at a few particular sequence problems. I'm going to grab these from your homework. I'm realizing now that I hadn't unlocked that homework, so I'm unlocking it in WebAssign at the moment. And this will be our last homework set. And we've looked at a handful of families of sequences, and it seems that the way your book is trying to get around the whole issue of not being able to play around with the concept of convergence is by having you like look at the first 5 or 6 terms of a sequence and then maybe look at the 100th term of the sequence and look at some graphs and see if you can get a feel for the general behavior. So I'll go at it the same sort of way. It's all partial sum stuff. So I might have to go in there and tweak those a little bit. But yeah, today we can start talking about partial sums of series. Pop open the .cam. Here we go. So we're going to revisit the basic ideas from last time, and then we'll expand on them a little. A sequence is a function whose domain is either equal to or a subset of the natural numbers. And depending on who you ask, particularly whether you're from continental Europe or not, you may include 0 in the natural numbers, you may not. I include 0 as a natural number. So a sequence can start with term 0 or can start with term 1. And there's a bunch of silly jokes about computer programmers counting from 0 and things like that. But for the purposes of notation and a lot of formulas, things are nicer if you allow them to start at n equals 0. However, they need not start at 0, right? Some sequences we saw yesterday started at n equals 1, had a first input value of 1, some had a first input value of 0, and in theory, you could have a sequence that started with the first input value of 20 or 1,000 if you wanted. A bunch of the basic things that we're going to play with just have to do with writing out a few terms of a sequence and trying to get a feel for what's going on with the thing. So I'll remind you of the terminology we used last time, but I'm not going to run through the definitions in quite the same level of detail. We'll just look at some examples and I'll ask you to classify them according to the stuff we were saying yesterday. So let's list the first 5 terms of the sequence an equals -1/2 to the n, where n equals 0, 1, 2, and so on. This is a special kind of sequence. This falls into one of the special families that we looked at yesterday. Does anybody recognize what kind of sequence this is? Which of those special families this lands in? The process of listing out the first few terms might help. So a0 is -1/2 to the 0. That's 1. a1 is -1/2 to the 1, which is -1/2. a2 is -1/2 squared, which is +1/4. a3 is -1/2 cubed, which is -1/8. a4 is -1/2 to the 4, which would be +1/16. So that's the first 5 terms, right? Terms 0 through 4 for this sequence. And you notice that to go from here to here, we multiplied by -1/2. To go from here to here, we multiplied by -1/2. To go from here to here, we multiplied by -1/2. And to go from here to here, we multiplied by -1/2. So in general, to move from one term of this sequence to the next term of the sequence, we're multiplying by -1/2. So in other words, this is what kind of sequence? Is my shit muted? No. Yeah. Anybody?
The Fibonacci guy?
It's not a Fibonacci sequence. So that's those are recursive sequences, right? Where you get the next term by adding up some combination of the previous terms. The other 2 families we talked about were arithmetic and geometric. Do you remember what?
Geometric.
Yeah,
Or,
geometric sequence. Yeah, because to go from one term to the next, we're multiplying by a fixed constant. Yeah, and so the name for sequences like that are geometric sequences. And the important bit of information to determine what a geometric sequence does is to figure out the size of the common ratio. So here the common ratio, that's that number you multiply by to go from one term to the next. So I would say this is a geometric sequence with common ratio r equal to -1/2. And at the very end of class last time, we talked a little bit about what geometric sequences do as n gets larger and larger and larger, as n goes to infinity. Here I would say, since the absolute value of r is the absolute value of -1/2, which is 1/2, which is less than 1, this sequence goes to 0 as n goes to infinity. And I want to just help you get a slightly better feel for what I mean by that. The notation, I'm going to go ahead and show you. And you'll be seeing this in the first week or two of Calc 1 when you talk about limits of functions. Here, when we say that this sequence, the sequence -1/2 to the n goes to 0, we write it like that. And so what this means is, as n gets closer and closer and closer to infinity, as n gets larger and larger and larger, 1/2 to the n gets closer and closer and closer to 0. You can see that pattern in the first few terms here, like 1 is further from 0 than -1/2. -1/2 is further from 0 than 1/4. 1/4 is further from 0 than 1/8. So as you walk down this list, these numbers are getting closer and closer and closer to 0. And the result we discussed at the end of class last time was that if the absolute value of the common ratio is less than 1, then the nth term of this sequence will get closer and closer and closer to 0 as n gets larger and larger and larger. And the way we say that, it's not notation that we officially use in this class, but I think it's worth showing you now. The way we would say that if we were being just a little bit more grown up about it is that the limit as n goes to infinity of this sequence, -1/2 to the end, is 0. And we can look at, Desmos doesn't do such a good job at graphing sequences, but Wolfram Alpha does. So I think I can generate for you a pretty nice looking plot here. I'm going to share that with you. Let's see what we get. No, I take it back. Wolfram also does not like graphing sequences. Okay, well, we'll plot it by hand then, that's fine. So I've got my first few terms. I can graph those. And then I'll try to show you visually what I mean by saying that that limit is 0, or that the sequence tends to 0. So up here, I'll mark this as 1. And I'll mark this as -1. This is going to be the graph y equals -1/2 to the n. And this is my n axis. And these I'm going to mark as 1, 2, 3, 4. And of course, 0 is over here. So a0, -1/2 to the 0, is right here. It's 1. a1 is -1/2 to the 1, which is -1/2. So a1 is right here. a2 is -1/2 squared, is 1/4, is right here. a3 is -1/2 cubed, is -1/8, is right about here. A4 is positive 1/16. It's right here. And so what you see if you look at all these dots, as you go further and further and further to the right, they're getting closer and closer and closer to the x-axis. And so if you were to put a little window around the x-axis, no matter how tight you make that window, eventually all the dots live within that window. Maybe the first few don't, like this guy, he doesn't, this guy, he doesn't, this guy, he doesn't. But this guy, this guy, this guy, this guy, and everybody from this point on is stuck within this little window. And if I were to tighten this window down and make it smaller, maybe I would kick out a few more. Maybe A3 and A4 would come out, but A5, A6, A7, there would still be all but finitely many dots inside that window. And that window is about 0, right? It's centered around 0. And so this is actually the visual definition of what it means for this limit to be 0, or for us to say this, is that no matter how tight you make this window, all but finitely many of these dots will be stuck inside of it. There will be some point. And from that point on, like from here on, all dots are inside. So Augustus Luz Cauchy was the first guy to really formalize this, and I'm doing my best to leave all the formal language out because, like I said, this isn't really a calculus class. We want to save that stuff because it's challenging for when that's the main focus, and that will be over the next couple semesters for you guys. But this is the picture, and this is the idea. And in order for us to move forwards with the discussion of sequences the way your textbook does, I think it's important that we have at least this basic idea. So we say a sequence converges to a number. In this case, this sequence converges to 0 if you can draw a window about that number. In this case, I drew a window about 0, such that no matter how tight that window is, all but finitely many of those dots are trapped inside the window. Right? That's what it means for a sequence to converge, or in this case, our textbook says for a sequence to have a limit. Now, there are all sorts of algebra rules and things we could talk about regarding limits. But the basic idea I want to get in your head is as n gets bigger and bigger, some sequences an get closer and closer to a fixed constant. So like -1/2 to the n, as n gets bigger and bigger, that -1/2 to the n gets closer and closer and closer to the fixed constant 0. It's this idea that's going to allow us to talk about the concept of an infinite series. So where we left off last time was with the introduction of this sigma notation. That if I have a big long addition problem like A1 plus A2 plus A3, and I send that all the way out to AN, so I'm adding up capital N numbers here. Each one of these things is just a number. A1 is a number, A2 is a number, A3 is a number. I can write this compactly as capital sigma little n from 1 to big N of A little n. If you want to, you can think of this as being like little n equals 1 to little n equals big N, if that makes it easier for you to understand the notation. But people don't usually write the little n at the top, they just usually write the number. So for example, sigma little n from 1 to 6 of 1 over n, that would be 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over 6. Now, off the top of my head, I don't know what that number is. Combining those as fractions would be a little bit unpleasant. We can go ahead and crunch it in Wolfram if we want. Yeah, it turns out to be 49 over 20. So as we talk more and more about series and this summation notation, we're going to take the basic idea from sequences and try to apply it to series. The place I want to get to is how could we make sense of an infinite series? Something like sigma n from 1 to infinity of 1 over n, which I would interpret as 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. But instead of stopping somewhere, going on and on and on like this forever. And the answer is right here. The answer to that question is going to be right here. But you have to combine this idea with this idea. This object right here, I would call a partial sum for an infinite series. And the ones we're going to be able to deal with best are geometric series. Those are series that are built out of geometric sequences. The infinite series, sigma little n from 1 to infinity, a little n, which is a1 plus a2 plus a3 plus a4 plus going on and on and on forever. This doesn't really have any meaning to us right now, because like we said last time, addition is a binary operator. It's something you can do 2 at a time, right? You have to do addition 2 at a time. Here I'm trying to do addition infinitely many at a time. And that is, of course, a big problem. I can go from doing 2 at a time to 3 at a time by just grouping them and doing the first 2 and then adding that result to the third. And you can induct on that and get to a place where you can do any finite addition problem kind of all at once. And the way we're going to try and get at understanding the idea of an infinite addition problem like this is to first chop it and look at a related finite addition problem, but then let the length of that finite addition problem get longer and longer and longer. So in other words, I'm going to define a sequence, and the behavior of that sequence as n goes to infinity is going to end up telling me something about the behavior of this series. So this is defined through, we call it the sequence of partial sums. So I'm going to use S for the sequence of partial sums. S1 is just A1. S2 is A1 plus A2. S3 is A1 plus A2 plus A3. You see where this is going, right? S4 is A1 plus A2 plus A3 plus A4. And in general, I like to use a capital N here. S sub capital N is A1 plus A2 plus A3 plus A4, all the way out to, the second to last term would be AN minus 1, and the very last term would be AN. Do you see how, as the capital N here gets bigger and bigger, this object gets closer and closer to this? In fact, I can write S sub capital N in sigma notation as the sum from n equals little n equals 1 to capital N of A sub little n. So as this guy gets bigger and bigger, this series, which is finite, so we can always compute it, gets closer and closer to whatever this thing should be. This is the big idea behind infinite series. This is how we end up defining what's called the convergence of an infinite series. So Sn is the sequence of little sums, where you add up just a few terms, and then you add one more term, and one more term, and one more term, and one more term. That defines a sequence called the sequence of partial sums. If this sequence of partial sums gets closer and closer and closer to some fixed constant, if the sequence, and that's the big deal here, is that to define the infinite series, you define some other sequence. If the sequence Sn, S capital N, gets closer and closer to some fixed number, call it S, as capital N gets bigger and bigger and bigger, then we say S is equal to the infinite sum. And we say that the series, and we call the series sigma 1 to infinity an convergent. A big chunk of Calc 2 is coming up with tests to figure out when a given series is convergent. Because as you might imagine, finding this thing can be a little tough, right? Finding and simplifying this thing can be a little bit tough. Like you saw in the example back here. What was it? I calculated, yeah, the partial sum of this series. Right, this calculation would take a bit of time. And to find a formula for this number in terms of this number would be tricky. But that's the goal. If you can do that, if you can find a nice formula for this thing in terms of capital N, then you can study Sn as a function of capital N. Capital N is a natural number. So this function of capital N is a sequence. This sequence of partial sums is what allows me to say whether or not the infinite series makes sense. I want to give you some concrete examples, and then I want to work an abstract example. But first, I'd like to take questions on these concepts, because these are pretty heady concepts. This is not something that is like ultra intuitive, I think. All right, so what are we wondering? What are we thinking? Questions about the notation. What symbols mean what, the difference between S and A, the difference between little n and big N. Those are things I see people get confused with often. Mostly all right?
What is the difference between the little n and the big N?
Think of them as just different variables. So little n tells you which of these numbers you're talking about, which of these a sub n's, which term of the series you're talking about. Big N tells you the length of the series that you're looking at. So s sub 4 here, capital N is equal to 4. And that says I'm going to add a1 plus a2 plus a3 plus a4. So it tells you how many of these guys you add up. And then little n is the marker that tells you where you are in the list for the a's. So remember, the a's are just a list of numbers. The s's are what we get when we add up some parts of that list. So S2 is what you get when you take the first two numbers from the list and you add them together. S3 is what you get when you take the first three numbers from the list and you add them together. So this is little n equals 1 plus little n equals 2 plus what you get when little n equals 3. And S3 says I'm going to add all of those up. I'm going to find out where I am on the list when little n is 1, where I am on the list when little n is 2, where I am on the list when little n is 3. Take all three of those numbers and add them up. That is S3. So that's the relationship between capital N and little n. Does that make sense?
Yes.
Let's look at a nice concrete example here, one that's not too hard to compute. I mentioned at the end of class last time that we were going to come up with some formulas. So let's find the first few, say, 4 partial sums for the series sigma little n equals 1 to infinity of little n. We're going to find S1, S2, S3, and so on. First, to get the notation clear, here, a sub little n is just n. So S1 is just A1 is just 1. S2 is A1 plus A2 is 1 plus 2 is 3. S4 is, S3 is A1 plus A2 plus A3 is just 1 plus 2 plus 3 is 3 plus 3 is 6. And S4 is A1 plus A2 plus A3 plus A4 is 1 plus 2 plus 3 plus 4 is 10. So that's the first few partial sums for this series. Let me just kind of recap this over here. S1 is 1, S2 is 3, S3 is 6, and S4 is 10. So imagine I take this list of S's. What do they appear to be doing? As capital N gets bigger and bigger and bigger, what does S sub capital N appear to be doing?
Getting bigger.
Mm-hmm. Yeah, exactly. It turns out that for this guy, S sub capital N, you can find a formula for it. It's capital N times capital N plus 1 over 2. Try it out over here. S1 is 1 times 2 over 2. That's 1. S2 is 2 times 3 over 2. That's 6 over 2 is 3. S3 is 3 times 4 over 2. That's 12 over 2 is 6. S4 is 4 times 5 over 2. That's 20 over 2 is 10. There's a great story behind this. it's actually coming from little Gauss. I don't know if you guys have heard of Carl Friedrich Gauss, but the way he came up with this is by saying, well, so why? First, the observation that the SNs are getting bigger and bigger and bigger here is correct. As capital N gets bigger and bigger and bigger, so let me, even before we do this, so as n goes to infinity, is Sn getting closer and closer to a fixed number? Look at this formula for Sn. If I put in bigger and bigger and bigger numbers for n, is this going to get closer and closer to any fixed constant, or is it just going to get bigger and bigger and bigger and go off to infinity? An easy way to understand this as n goes to infinity thing is just imagine plugging a huge number in for n, something enormous. If I take an enormous number and I multiply by that same number plus 1 and then divide by 2, I'm going to get an enormous number out, right? This isn't going to get closer and closer to some finite value. As n gets bigger and bigger, Sn, which is n times n plus 1 over 2, also just gets bigger and bigger. So I would not say that this series converges. So I'd say hence sigma little n equals 1 to infinity of little n does not converge, because its sequence of partial sums just gets larger and larger and larger. It just runs off to infinity. Remember, we said that a series, an infinite series, is convergent if, as n gets bigger and bigger, Sn gets closer and closer and closer to some number. So if the sequence Sn gets closer and closer to some number as n goes to infinity, then we say that the infinite series from which Sn is built is convergent. For this example, that's not true, because as n gets bigger and bigger and bigger, Sn also just gets bigger and bigger and bigger. It's not getting closer and closer to some fixed number. Do we feel like we understand this idea, the relationship between the Sn's and the An's, the series here? It's not super easy stuff to understand, and if this isn't clicking immediately, don't feel bad. I've got plenty of Calc 2 students who don't wrap their heads around this stuff. At least not for the first few weeks we talk about it. But the fundamental thing we're trying to get around is that I can really only do addition 2 numbers at a time. So if I want to know what does it mean to add up infinitely many numbers, I have to think about that in terms of something finite. And the SNs are the finite things I think about the infinite addition problem in terms of. As capital N gets larger and larger and larger, these partial sums get closer and closer and closer to the infinite series. If these partial sums get bigger and bigger and bigger, they don't approach some fixed finite number, then I don't say that the infinite series has a fixed finite value. I would say that the infinite series diverges or is infinite. So there is a fun story here. Why is the Sn from the previous page, which is 1 plus 2 plus 3 plus 4 plus whatever, all the way out to second to last term is capital N minus 1, last term is capital N, equal to n times n plus 1 over 2. So Here's the story. Little Carl Friedrich Gauss, growing up in Germany, was a very precocious little kid. Precocious, you know, he just liked to shout out answers a lot in class, which is a wonderful thing. Usually teachers have a hard time getting people to respond at all. But baby Gauss was one of those people who totally takes over a classroom and doesn't let anybody else talk. So in order to shut up baby Gauss up for a minute, his second grade teacher said, "Hey, baby Gauss, why don't you go off into the corner and add up all the numbers from 1 to 100 real quick," thinking that this would keep baby Gauss busy. Not only did baby Gauss return with the answer 5050 right away, he also had a general formula for adding up the first n numbers. It was this. And the way he came up with it is by saying, okay, well, let's look at the sum. So I'll write the first 4 terms, and then I'm also going to write the last 4 terms. So I'll write n minus 3 plus n minus 2 plus minus 1 plus n. All right. This is a big addition problem where I'm adding 1 plus 2 plus 3 plus 4 all the way out to capital N. So I'm adding up the first capital N numbers. He groups them. Like we were saying, you got to do addition 2 at a time. So the easiest way to understand a big addition problem is to find a clever way of thinking about it as a collection of finite ones. He says, okay, this is 1 plus n, the outside terms, and then plus 2 plus n minus 1 plus, then working your way in, 3 plus n minus 2 plus 4 plus n minus 3, right, and so on. Each one of these is equal to n plus 1, right? 1 plus n, that's n plus 1. 2 plus n minus 1 is also n plus 1. 3 plus n minus 2 is also n plus 1. 4 plus n minus 3 is also n plus 1. How many terms like this do you have that we're adding up? Well, there's n numbers here, and I'm grouping them into sets of 2. So there's n over 2 such pairs. So altogether, here you end up with Sn, you end up with 1 plus 2 plus 3 plus dot 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 all the way out to n is equal to n over 2 copies of n plus 1, which is n over 2 times n plus 1, which is the same as n times n plus 1 over 2. And that's how baby Gauss solved this problem, and that's still the proof that we give in analysis classes today. This is an n times n plus 1. Sorry, that's hard to read, isn't it? So this is one of the few series for which we can find the partial sum, right? If a sub little n, the things we're adding up, are just equal to n, in other words, you're wanting to add 1 plus 2 plus 3 plus 4 plus 5, on and on and on forever, that goes to infinity. Because if you add up the first n numbers, it's equal to this. And as n goes to infinity, this goes to infinity. So it's something we should have some intuition for, right? The series 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, on and on to infinity, that should go to infinity. Because I'm adding more and more bigger and bigger shit, and I'm doing that forever and ever and ever. So yeah, that shouldn't be a convergent series. That should make intuitive sense. But if we want to try and understand what infinite series really are, the key is to wrapping our heads around this concept of a partial sum. So what I like about this example is because we have a basic intuition for this series. If I let capital N go to infinity in this expression, I should get infinity. Because this thing is big, I'm adding up a bunch of big shit. And as I add more and more and more, bigger and bigger and bigger shit, I should get bigger and bigger and bigger numbers out. And if you let me do that forever, or out to infinity, whatever that might mean, that should be infinite, that shouldn't be finite. But here we see the structure, right? Here we see the y. This is how we how we understand all series is through this lens. And so understanding the series for which we have good intuition through this lens is a good way to get ready to understand other series which might not be as intuitive. I claim that the thing that makes this one intuitive is that the stuff you're adding up on its own gets big. If you add more and more and more, bigger and bigger shit, you're just going to get bigger and bigger shit out. But what if the stuff you're adding up gets small? That's where things become challenging. And this is where my next favorite example for introducing infinite series comes in. And this is called a geometric series. So a series from, say, 0 to infinity of an is called geometric if the sequence an is a geometric sequence. So geometric series is one that adds up all the terms of a geometric sequence. Reasonable naming scheme. For example, the sum from 0 to infinity. Let's look at 1/2 to the n. Is there a question? All right, first, let's see if we can try to understand what this means. It should be 1/2 to the 0, plus 1/2 to the 1, plus 1/2 to the 2, plus 1/2 to the 3, and so on, forever and ever. We've studied the sequence to the n, or we studied like the other day, something like that. And we know that this is a geometric sequence, right? Without the sigma, just 1/2 to the n, that's a geometric sequence. And the common ratio there is smaller than 1 in absolute value. So I know that these terms, as you go further and further out, get smaller and smaller and smaller, right? Like this is 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32. So as you go further and further out, I'm not adding bigger and bigger shit. I'm adding smaller and smaller shit, which makes it a little bit harder to guess what this series is going to do. We're going to come back to this, but I want to develop, so can we find a formula for the capital N partial sum of this series? So Sn here is the sum from little n equals 0 to capital N of 1/2 raised to the little n. That's like this sum, except it doesn't go on and on forever. It stops somewhere. This guy stops somewhere. This is 1/2 to the 0 plus 1/2 to the 1 plus 1/2 to the 2 plus, but then it stops eventually. The second to last term is 1/2 to the capital N minus 1. And then the very last term is 1/2 to the capital N. As capital N goes to infinity, this thing gets closer and closer to this thing, right? Just compare these two. That's one of the reasons this notation is so nice. As this capital N gets closer and closer to infinity, should be getting closer to this thing. So if you want to ask a question, if you want to say, go ahead and unmute your mic. Otherwise, let's keep them muted because we're getting some feedback. Yeah, that should do it. All right. So this object, as capital N gets closer and closer to infinity, i.e. gets bigger and bigger and bigger, should be getting closer and closer to this object. If I can find a nice clean formula for this object, that will allow me to try and interpret this thing, because this thing is the same as this thing with capital N equal to infinity. But right now, in this form, it's very hard for me to say what this thing does as capital N gets closer and closer to infinity. So to do this, I will work with the more general formula n equals 0 to capital N of just r to the n. So the formula above, the thing we're looking for, is what you get when you plug r equals 1/2 into what I'm going to do down here. All right, this is r to the 0 plus r to the 1 plus r to the 2 plus r to the 3. The second to last term is r to the capital N minus 1, and the last term is r to the capital N. And this is like your general geometric series. R to the 0 is 1, r to the 1 is r, so usually you'll see this written as 1 plus r squared plus r cubed. Second to last term, r to the n minus 1, last term, r to the n. And this is the thing that I'll call Sn for now. Right? Maybe to avoid confusion. No, let's do it. So this Sn has r's in it. If you plug in r equals 1/2, this Sn becomes this Sn. I'm going to come up with a general result for geometric series, and then I will apply that result to the example we were looking at above. The trick to doing this, to finding a nice formula, basically I want to simplify this, right? You can think of this as like a big ass polynomial. It looks like a polynomial, just has r's instead of x's. So if there's some way for me to like factor it or simplify it or something like that, that's what I want to do. But it's difficult. It's very difficult. And there's a trick. There's a trick that I haven't seen used anywhere other than this, but is always used here. It's just to multiply by 1 minus r. If I take 1 minus r times Sn, that's going to be 1 minus r times, well, what's Sn? It's 1 plus r squared plus r cubed plus second to last term is r to the cap n minus 1, last term is r to the cap n. Now I'm going to distribute this 1 minus r over this term. When I multiply the 1 through, I'll just get 1. I'll write it all out, 1 plus. And then I'll have minus r times that. Okay, so I'm a little short on space there, but you see what I did from here to here? At this line, I'm like, fuck it. For whatever reason, I'm just going to multiply Sn by 1 minus r and see what happens. So here's 1 minus r times here's Sn. I'm going to distribute this over this. That means I'm going to multiply this all by 1, and then I'm going to subtract what I get when I multiply this all by r. I'm going to put my equal sign down here so I've got more space. When I multiply all of this by 1, when I distribute the 1 over this sum, I just get that sum. That's 1 plus r squared plus r cubed out to r to the n minus 1 plus r to the n. And then from that, I'm going to subtract what I get when I distribute this r over this. So that's minus, I'll put some parens in to help us see where each piece is coming from. This minus is this minus, and now I'm just going to distribute this r, one term at a time. R times 1 is r. R times r is r squared. R times r squared is r cubed. R times r cubed is r to the 4. And then the second to last term here, r times r to the n minus 1 is r to the n. and then r times r to the n is r to the n plus 1. So when I multiply Sn by 1 minus r, I get all this minus all this. And that's nice because there's a shitload of cancellation. The 1 from this first term survives, but then I've got a plus r minus r, plus r squared minus r squared, plus r cubed minus r cubed. The next term in here, and these dot dot dots, is plus r to the 4, and then I've got a minus r to the 4. This comes all the way out to here. The second to last term in this, or the term right before this, in these dot dot dots, is r to the capital N minus 1. So that will swallow up this guy. Then you've got plus r to the n minus r to the n. So what survives is just 1 minus r to the n plus 1, which is a really nice algebra trick. So you get that 1 minus r times Sn is equal to 1 minus r to the n plus 1. So 1 minus r times Sn is equal to 1 minus r to the n plus 1. Now divide both sides by 1 minus r. This means the formula for Sn, the formula for the nth sum of any geometric series, is 1 minus r to the n plus 1 divided by 1 minus r. Beautiful, right? So this is one of the first major results in the study of infinite series. I believe this was done back in ancient India, like a long time ago, even before the Arabic Revolution that brought us modern algebra. This result, I believe, was known. So what does that mean? Well, let's return to the example that we started with, the 1/2 to the n series. If S is the full infinite series, sigma n from 0 to infinity, 1/2 to the n, this is geometric with r equal to 1/2. So if this is true, then if S is this series, the series that I'm wanting to play with, then Sn is the sum from n equals 0 to capital N of 1/2 to the little n, which according to what I just found is 1 minus 1/2 to the n plus 1 over 1 minus 1/2, like this. And as n gets bigger and bigger and bigger, as capital N goes to infinity, what does this do? Well, this piece right here is just 1/2 times 1/2 to the n. And the major result at the end of class last time was that this piece, since r is less than 1 in absolute value, 1/2 to the n, r to the n, is going to go to 1/2 times 0, right? This 1/2 is this 1/2. But the 1/2 to the n, he's going to go to 0. Therefore, as capital N goes to infinity, Sn, which is sigma n from 0 to cap n of 1/2 to the little n, this goes to 1 minus 0 over 1 minus 1/2, or 1 over 1 minus 1/2, which is 2. So we would say that the infinite series the thing we called S the infinite series from 0 to infinity of 1/2 to the n converges to 2. In some places, we would just write is equal to. Sometimes we just write sigma n from 0 to infinity 1/2 to the n equals 2. So whichever you prefer is okay. Some people prefer to never call those things equal, just say that the one converges to the other, because this is an infinite process. You'll never actually finish adding up all of those things, but if you could, you would get 2. And I'd like to, I think we're probably getting a little close to time here. The last thing I wanted to do with you guys today is to show you why this is called a geometric series. So we said a geometric series is a series that's built out of a geometric sequence. That's all well and good. But where does the name come from? And the reason these series have been known for so long is because there is a simpler way to think about them, purely in terms of geometry. I'm going to take a box here. I'm going to call that side length 2. I'm going to call this side length 1. So I declare this side length to be length 2, this side length to be length 1. And I'm going to chop it in half. Then this guy has area 1, and this guy has area 1. So if I chop him in half, this guy has area 1/2. And this guy has area 1/2. If I chop him in half, then this has area 1/4, and this has area 1/4. And if I chop him in half, then this has area 1/8, and this has area 1/8. So if I chop him in half, this has area 1/16, and this has area 1/16. You see what's going on here? The total area is 2, because it's a rectangle, and the height is length 1, and the width is length 2. So it's got to be total area of 2. But we can also think of it as this area plus this area plus this area plus this area plus this area. That's 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, and so on forever and ever. And this is sigma n from 0 to infinity 1/2 to the n. So this is why people have known for thousands of years that these geometric series do what they do, because you can think of them in terms of pictures, right? I can take this box here that clearly has area 2 and chop it up in this clever way to interpret that area as 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, and so on. Pretty neat shit, right? That's where the term geometric comes from. All these geometric series can be thought of this way. I could have started with a 3x1 box and then proceeded to show you where the series sigma 1/3 to the n comes from. I could have started with an r/1 box and chopped that up by ratios of r and shown you where the series sigma r to the n comes from. But I think making it nice and concrete like this is the way to start to understand it. From an analytic perspective, from the perspective of algebra and calculus, it's all about partial sums. And that's the part that is, for most folks, hardest to understand. Like, what the fuck is Sn, and what does it have to do with this infinite series? The key to keeping that straight is just remembering this definition. This is the connection between sequences and series. If you want to define an infinite series, because the addition problem you're talking about goes on and on and on forever, we have to do so in terms of some finite process. I can't add a1 plus a2 plus a3 plus a4 all the way out to infinity all at once. I don't even know what the hell that means, because addition is something that has to be done two at a time. So I break this big, long addition problem down into a bunch of smaller ones. And each of these smaller addition problems is finite, so I can handle them. And then I ask, if I look at this sequence of finite addition problems, do those start to form any pattern? As I look further and further out along the list of partial sums, do I notice them getting closer and closer to some fixed number? If I do, then I say that has to be the infinite series, whatever it is. Even though I don't know what it means to add infinitely many things together, as I add more and more things together, I'm getting closer and closer to some number. So I just declare that number to be the value of the infinite series, and I call the series convergent. It can be tricky to wrap your head around, and so the homework that I guess I forgot to open for you guys yesterday, but I'll go ahead and pop for you right now, on sequences and series, starts off with, here's some sequences, list the first few terms, or graph the sequence, or say what the sequence does as n gets bigger. Those are fun, intuitive things. But then the last few problems are going to be calculating partial sums and making guesses about what's going on with the full infinite sum. And then finally, there will be some problems having to do with infinite geometric series. So there is a kind of end result here that I can share with you. This is where we will wrap it for today. So if S is an infinite geometric series, and I'm going to include the a naught instead of just the r to the n here, because remember, a geometric series is a geometric sequence is a starting term times the common ratio to the n. And remember that this is the same as a naught plus a naught times r plus a naught times r squared plus a naught times r cubed plus so on forever. I can factor this out. I can factor the a naught out. And I get exactly the object that I just learned about. This is the same as a naught times sigma n from 0 to infinity, just r to the n. So if this is a geometric series, and the absolute value of r is less than 1, then Sn is, I can factor the a naught out, remember, so this is going to be just a naught times whatever the Sn is for this piece, which is a naught times 1 minus r to the cap n plus 1 over 1 minus r, goes to a naught times 1 over 1 minus r as n goes to infinity. And we say that the series sigma n equals 0 to infinity, a naught times r to the n, converges to or is equal to a naught times 1 over 1 minus r. Right, is a convergent series. For those of you who intend to go on to Calc 2 or go anywhere that involves a meaningful amount of analysis, series will be hugely important. Even at the end of Calc 1, you'll talk quite a bit about series as they relate to Riemann sums and integrals. To understand infinite series, you must first understand infinite geometric series. This special kind of infinite series is like the backbone around which we build all of our theory for infinite series, because they're fairly easy to work with, because the algebra is nice. Namely because we're able to get this nice formula for the nth partial sum. Because we're able to get a nice formula for the nth partial sum, we're able to say what happens as n goes to infinity. And as capital N goes to infinity, the nth partial sum is the infinite series. And so I'm able to say that the infinite series, as long as the absolute value of r is less than 1, this is important, has to be absolute value of r, has to be less than 1. As long as that's true, then this big, long, infinite addition problem can be made sense of. And this is what you get out. How are we doing for time? Do we have time for one more example? We do. Grab one from your homework. Sum of an infinite geometric series. Yeah. Oh yeah, this is a good one. .9 repeating. We've all seen the silly Facebook memes that try to justify that this is or is not equal to 1. I'll spoil it for you. This is equal to 1, and there's a reason for it. Because this is 0.99999 on and on forever, which is the same as 0.9 plus 0.09 plus 0.009 plus 0.0009 plus, and so on, forever. Right? That's just how the arithmetic of decimals works. If you add these first two, you get 0.99. If you add these first three, you get 0.999. If you add these first four, you get 0.9999. If you were to add fives, you get 0.9959. And if you want the nines to go on and on and on forever, that means you're looking at the infinite series, which is the same as sigma n from 1 to infinity. Maybe, oh, I could write this as coming from 0 to infinity. Let's do it like that. 0 to infinity, 0.9 times 10 to the negative n, or 1/10. I'll write it like this. Let's write it like this, times 0.1 to the n. In other words, this is sigma n from 0 to infinity, 0.9 times 1/10 to the n, which is a geometric series. I can pop out the 0.9, same as we did above. This is 0.9 times sigma n from 0 to infinity, 1/10 to the n. And that is a geometric series. Sorry, I'm using scratch paper here. That is a geometric series with the absolute value of r being the absolute value of 1/10, which is 1/10 is less than 1. So I can use my formula. This should be equal to a naught, which is 0.9, times 1 over 1 minus 1/10. Well, that's 0.9. 1 minus 1/10 is 10/10, minus 1/10 is 9/10. So this is 1 over 9/10. 0.9 is 9/10. So this is equal to 1. So the infinite repeating decimal thing you can resolve using geometric series. It's just one fun example of cool problems that you can solve using this formula we just cooked up for geometric series. The important thing to make sure the series is finite is this part, that r has an absolute value less than 1. If you want to add 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3 plus 2 to the 4, that series isn't going to converge because you're adding 1 plus 2 plus 4 plus 8 plus 16. You're adding stuff that just gets bigger and bigger and bigger. But if the stuff you're adding up gets smaller and smaller and smaller, and it gets small enough fast enough, then the infinite series can converge, can yield a finite value. There's many different ways of interpreting what it means to add infinitely many things together, But the thing that I've shown you here today is the standard way of interpreting that. And again, that's this. So this is the definition of a partial sum for a series. The first partial sum is just the first term. The second partial sum is the first term plus the second term. The third partial sum is what you get when you add up the first 3 terms. And the nth partial sum is what you get when you add up the first n terms. So the infinite series, the series where you add up all of the terms, the infinitely many terms, should be the limit as capital N goes to infinity of the nth partial sum. And that's the standard, or at least first way, to interpret an infinite series. There may be other ways to do it. There are other ways to do it, and you'll learn those if you decide to study mathematics in graduate school. But for most human beings who have ever thought about the question carefully, this is the answer they come up with. This is the kind of globally acknowledged answer to how to understand an infinite series. So your homework this week is first going to be just playing around with sequences, trying to get comfy with the notation. And then you're going to start playing around with partial sums. And then after you play around a little bit with partial sums, you will start answering some questions about infinite series. Tomorrow I want to talk about the algebra of the sigma operator. So there are some things that we can do. Like here on this last example, you saw me take this 0.9 and move it from inside the series to outside the series. What I'm really doing there is factoring. I'm factoring the constant out just like I did from here to here. But there are some other operations like that which we can do, and it's nice to get comfy with them in the sigma notation. And then the last thing I want to do is cook up some formulas, like the n times n plus 1 over 2 formula that we started class with today. There are some similar formulas like that which will be useful to you at the end of Calc 1 when you talk about Riemann sums. And I want to make sure I've given you everything that you need to be successful when it comes to those things. So tomorrow will be the algebra of the sigma operator, and then some more special series. These will not be infinite series. These will actually be finite series that we're going to play around with tomorrow. But the geometric series stuff is the simplest form of an infinite series. And so this is about as deep as we're going to go with infinite series. But there'll be a little bit more to do with sigma operator. Maybe we get to talk about the binomial theorem if there's time. But then that will be the end of our class. That will be the end of MAC1147. So you can sigh a breath of relief and start preparing for the final exam. I know some people have expressed a desire for a study guide for the final exam, and so I'm going to put together a little quiz. Exam 4, our last exam, is not going to have a study guide. It's a take-home exam, so I don't think we really need a study guide for that. You'll be able to work it in your own time and your own pace, and it's, of course, open note, open book, go ahead. Just don't use the internet or talk to anybody else, and I'll hand out the exam 4, the take-home, I'll hand out on Thursday.
Will we be getting any more homework?
There's going to be a homework on sequences and series that's going to pop open now. I opened that for you yesterday. I just didn't get to it. So I'm going to open that up now right after class, but then that will be the last homework.
Okay, and then I requested an extension for till the 23rd, but I had to change it to Friday.
Okay, let me get
I put in two extensions because I had to change it to Friday, the 24th.
Well, I've got you here now. Let me go ahead and make sure I answer that extension request in the way that you want. Let's see. Yeah, okay. So you wanted that until the 23rd. When is our final in this class?
The 30th.
30th? Okay, I'll just push these to the 30th. So there's a bunch of other people who wanted an extension on that homework also. So I'll go ahead and respond to all those now, and I'll just push them straight to the 30th so you guys can work on that stuff as long as you want. If you want,
awesome, thank you.
So you can play around with them or go back and look at them in preparation for the final. Please just let me know. You can submit the request on WebAssign, and I will get to it as soon as I can. Today I will make sure to answer everything that's in there now. So if there's something that you want extended for the purposes of review, go ahead and submit the request. And as soon as I finish popping open your current homework for this week, I'll go through and clear out those extension requests, okay? Any other last minute things before we wrap it up for today? Between big N and little n. Big N is the length of the partial sum you're looking at, little n tells you which number from the list you're adding up. So a sub little n are the things you're adding up. Big N is the number of those things that you're adding up. Any other last minute sort of questions, curiosities, anything like that? Okay, then I'll go ahead and end the meeting here for today. And I will post this up to YouTube and try to get your guys' extension requests all answered in the next few minutes. If you do need anything, reach out to me on Canvas. Remember, I'm going to be giving out the take-home exam this Thursday, and you'll have until the 30th to wrap that up. And then on the 30th, we'll do our final, which is going to be run very similar to exam 3. All right? Have a good afternoon, guys. Of course, yeah, you too.